Well, hello everyone. It's about 3:30 in the morning, I guess, on Friday morning, and there's sickness that has visited my house, so I've been up all night with my wife. But I promised you guys I would give you a review session, and I think it's important for me to keep my word. So I'm hoping that this video makes it to you, and I'm sorry that I wasn't there in person to give it to you, but I hope that it helps with scientific notation. So you came to do this session on scientific notation, and that's what we're going to do. This is part 3, so we've already done significant figures in the very first episode, and then of course in the second episode we did dimensional analysis and conversions of units, and so now we're going to take a look at scientific notation. Now I'm looking through the original lesson that I taught on this in chemistry, and I want to catch up to the spot right here that is relevant to what we wanted to talk about today. Whether you're in chemistry or you're in physics, you're going to deal with very large and very small numbers. And that usually means a number with a lot of zeros either in front of it or behind it. It becomes very cumbersome to work with, to calculate with, to put into a calculator, to write down on a piece of paper. And we end up counting one another's zeros just to see what the value of the number is, and then it's very easy to make mistakes. In fact, you've seen right here that I've grouped my zeros in groups of 3. And if the zeros are before the decimal on the left-hand side, they've got commas. If they're after the decimal, well, I've just put a space between sets of 3 so that you can count them rather quickly. And here we see the number of atoms in 1 gram of hydrogen, which is absolutely astonishingly enormous. Or the flip side, the mass of 1 atom of gold in grams, which has so many zeros after the decimal place before you get to anything that's not a zero that it just seems overwhelmingly small. So in both of these cases we wanted to use a technique that takes away the cumbersome nature of writing a number like that and write in something called scientific or exponential notation, which was developed to be able to handle these kinds of numbers rather easily. Now, it's only going to be easy if you understand the rules, and this is where some of the mistakes that were showing up in the diagnostic were coming from. First of all, scientific notation is written as the product of 2 numbers. So you've got a coefficient called m, and that number is always in the front, and then it's raised to a power, the 10 is raised to a power, and that number n needs to always have a certain set of criteria. So we're going to look at m and we're going to look at n. First of all, the rules for m. I've seen this error quite a bit from some of our class, so we want to make sure that this is understood. The number in the front has to be a number somewhere between 1 and 10, and it can be equal to 1. You see that down here, but it cannot be equal to 10. So it can be 9.99999, but it cannot be equal to 10. So m is pinched between 1 and 10. If we were, by some stroke of for whatever reason, we were to get the number 10, we were going to have to adjust it so that it ends up looking like a 1. And that's what happened if we actually ended up with a 10. Okay? So that's the rules for m. Now the rules for n, as the exponent, is that these numbers have to be whole numbers. Now math doesn't demand that of us. Math can have fractional exponents and different kinds of exponents that we have in scientific notation. But in this class, n has to be a whole number. But that does not mean it can't be 0 or it can't be negative. So it could be positive, it could be negative, and it could be 0. Okay? Now, let's take a look at an example. Here is the number 84,000, and to write it in scientific notation, the result will come out to be 8.4 times 10 to the 4. The question is, how do you get there from here? So you would want to go up to your 84,000 and locate where the decimal is written currently, which is right there. Okay? Well, then you want to take that and you need to try to get from that number to a number that's between 1 and 10. I don't know why I'm getting that menu. Okay, so then you want to move this. Why are we not writing? Move it to the left until you get to the 8.4 right there. Now you need to count how many spaces you move toward the left. So that was 1, 2, 3, 4. That becomes your exponent power of 10 right there. I think most of us were pretty decent at turning a number that is written in standard notation into a number in scientific notation. Okay, 10 to the 4 means actually 10,000. So 8.4 times 10,000 would give us this 84,000. That's the way we would get back and forth between the two numbers. So in this case, the number in the front was the M number, and that's called that's the 8.4 number. And then the exponent in this case was the 4. Okay, and that tells us how many times the coefficient 8.4 needs to be multiplied by a power of 10 to get back to the original number 84,000. Okay, so that's the way the scientific notation works for large numbers. So if you're writing a number greater than 10 in scientific notation, then your exponent is equal to the number of places that your decimal point had to be moved to the left. So here we have a number 6,300,000. If we want to write this number in scientific notation, we have to again locate where is the decimal point now, and it's right there. Okay, and then we're going to head to the left 3 spaces, 6 spaces until we get to a number 6.3, which is between 1 and 10, and then take the number of spaces we move to the left, and that becomes now our exponent in the power of 10. Same with 94,700 here. Now I do want you to notice that all of these zeros disappeared in the scientific notation. If you know your significant figure rules from the prior lesson, you know that these zeros are placeholding zeros, that there's no decimal written there, and therefore they are not significant. But if we had placed them behind the 3 after the decimal point, they would be significant. Zeros that are final zeros after a decimal place are significant. But that would change the precision of our number, even if it didn't change the value, and we can't change the precision just by writing it in scientific notation. So the zeros don't belong in this case. Now when we take a look at a few here soon where the zeros do belong. So in this example right here where we have 94,700, the 2 zeros are not significant. There's no decimal place marked, and there's no zeros after it. So those zeros are placeholding zeros and not significant. Therefore, when we move backwards, and we go 4 spots backwards in this one, we only keep those parts that were significant to begin with, the 9, the 4, and the 7. This is why you see this written this way, 9.47 there. Okay, so I hope that made things a little more clear. Now, if you're looking at a tiny number, a number that's smaller than 1, then it's going to have a negative exponent when you write it in scientific notation. So here's an example, a decimal number over here, 0.0025, this one. And we want to write that in scientific notation, and we find that where the decimal place is located now, right there, and we need to move it until we get a number between 1 and 10. So this time we're going to have to move it to the right, not to the left. So we're going to go this way. Now I just moved 4 places toward the right to get to a number 2.5, which is between 1 and 10. But because I moved it to the right, the exponent now is negative. Okay? It's actually true that 2.5 is bigger than the original number. 0.00025 is a tiny number. 2.5 is bigger than that. So to make sure that this is actually the same size as the original, we need to multiply by a number that makes it very small. And 10 to the minus 4 is 1/10,000th, which is now multiplied by 2.5. Okay, so the negative exponent, -4, will indicate that our coefficient, which is 2.5, has to be actually divided 4 times by 10 to get the original number that we were looking at, which was 0.00025. Okay, so these two numbers down here are equivalent, and this one is in standard form, and this one is in exponential or scientific notation. All right, so that's how to write the numbers in scientific notation, moving the decimal to the left and to the right. And I believe we just said that, so that's just repetitive. Here are two examples of decimal numbers who end up in scientific notation, and I do want you to make sure that you don't write this one like 73.6 or something like that. The number's got to be between 1 and 10. Alright. What happens if you have two numbers that are in scientific notation and you need to do math with them? Well, it depends on what you need to do to them. If you're going to add or subtract numbers that are in scientific notation, you have to take care of some business first. Alright? First, those two numbers have to be written to the same power of 10. And if they're not already in the same power of 10, you will have to adjust them until they are. Then, after you get that done, check mark, then the factors should be added or subtracted in the front, those numbers in the front, and then multiplied by the same power of 10. Let's come down here and see an example. 4.5 times 10 to the 6 minus 2.3 times 10 to the 5. Can I just take this 4.5 and subtract the 2.3 from it? Answer, no. They're not in the same columns if you were to write them out in standard form. Why? Because one's multiplied times 10 to the 6 while the other one's multiplied times 10 to the 5. So in order for this to work, you're going to either have to decide to write the first term as an exponent times 10 to the 5th, or you can adjust the second one to be times 10 to the 6th. That's your arbitrary choice. Doesn't matter which one you'll do, or which one you do, you'll still get the right answer. In this case, they've decided to take the 10 to the 6 number and write it as 10 to the 5. So this number came down in size from 10 to the 6 to 10 to the 5. And just to make sure that the entire value doesn't change, then this number goes up by 10. Now immediately some of you are going to say, yeah, but that's not in scientific notation. Yes, that's absolutely correct. We took it out of scientific notation. 45 is too big to be in scientific notation in the front. But we did it on purpose so that we could subtract. So now that this 10 to the 5 is the same as this 10 to the 5, we're going to leave the 10 to the 5s alone for just a second. We're going to take the 45 and subtract the 2.3 from it and get a number. That'll be the 42.7 right here. And then we'll multiply that answer times the exponent of the power of 10 that they both share, which was 10 to the 5 here. Now this number is actually correct now. 42.7 times 10 to the 5 is the right size of number, but that number is not written in scientific notation because 42.7 is too big in the front. Okay, so we either write it as 4.27, in which case we made this get 10 times smaller than it was, and we'll have to adjust this to get 10 times bigger, which is what they've done here. Make this one more power of 10 bigger and bring the exponent to the left once here so that it's in scientific notation. I'm trying to figure out why they ended up with the 3 here. And I don't see any reason why they should have done that. I think it should be 4. Let's see. Let's do our subtraction rules and scientific and significant figures. It was 45 minus 2.3. So we're looking at 42.7. Here's why. They marked this column because it didn't have anything over here. This column has to be the column in which the answer is recorded. So that's where they stopped, 43. Of course, 43 is still too big for scientific notation, so they came over here and made it a 4.3, right? And changed this exponent to match. So there's a little bit of work here to do. After you subtract it, sometimes it's already in scientific notation when you subtract it. Other times you have to do some work before it is. Okay, if you're multiplying two numbers with scientific notation, you do things a little differently. To multiply two numbers that are in scientific notation, you will multiply the first factors. Here's an example, and by the factors we mean the numbers in the front, so that number there and that number there. Multiply 3.1 times 5.01. Then you will go into your powers of 10, hold the base, add the exponents, and express as a new power of 10. So you can see this real quickly. The 10 to the third, 10 to the fourth get added together. We'll have 10 to the 7th, which happens here. And then 3.1 times 5.01 gives you, well, it doesn't give you 16 exactly. You have to use your significant figure rules to decide. You only need to keep 2 sig figs from the multiplication rules out of this. But it rounds to 16. 16 is what they kept. Now the value is correct, but it's not written in scientific notation, so we need to adjust this number to be 1.6. But in doing that, we actually made it 10 times smaller than it was originally. So we need an extra 10 to be inserted over here. And that's where it comes in on the 8. 10 to the 7th now became 10 to the 8th. Okay, so the process was multiply the factors, hold the base, and add the exponents to the power of 10, get your answer, apply the sig fig rule. Once you have it written there, if it's already in scientific notation, you leave it alone. But if the factor in the front is too big or too small, you'll have to adjust this number and then move powers of 10 into this number to adjust. So 16 was too big, we went down to 1.6, we had to take the extra 10 we took away and stick it in the power of 10. That's why we have 10 to the 8th. Okay, if you want to divide numbers using scientific notation, to divide two numbers that are scientific notation, this time you're going to divide the first factors. So here's a 7.63, divided by this 8.6203. So we're going to divide those two factors. Then we're going to take our powers of 10 that are right here. We're going to hold the base and subtract our exponents. We got a 3 and a 4 right there. So we'll punch into a calculator 7.63 divided by 8.6203 to do that part. But 10 to the 3 minus 4 is pretty simple. That's 10 to the negative 1. So that part we don't need a calculator for. That's already been done. Now when we push this part into a calculator, 7.63 over 8.6203, we're going to get a number on a calculator. It may have a whole lot of digits, but we need to take a look at our significant figures here and decide how many to keep. And here we would differ from them in what they decided to keep, because I see 3 sig figs on the top and 1, 2, 3, 4, 5 on the bottom. The lesser of 3 and 5 is 3. We should have kept 3 significant figures here, not 2. You should be able to diagnose that mistake that they made. And then, once again, this number is not big enough to be in the front in scientific notation. It needs to be between 1 and 10, and 0.89 is smaller than 1. So we moved the decimal place over to get it 8.9, but in doing so we made it 10 times bigger than it was originally. So we need to make our power of 10 10 times smaller. So you'll see 10 times smaller means the negative 1 here becomes a negative 2 after we've made the adjustment. Okay, so this is how you do multiplication and division with scientific notation. And of course earlier we did addition, and the subtraction rules are the same as they are for addition. Put those 4 things together and you'll be able to work with scientific notation in practice. Okay, I just want to spend just a couple of seconds here on accuracy, precision, and error. And if you're already running out of time, if this video got started late or whatever and you need to go to class, this can be stopped here and you can look at it again when you get home. we'll post it up on the internet for you. Accuracy, precision, and error have to do with terms that have to do with both the exactness and the correctness of measurements that we do in the laboratory. And they sound like they mean the same thing. But in chemistry and physics and any other science, accuracy tells us how close we are to what we were really trying to get to. And so we would say if we're accurate, if we're actually close to the real value. But precision really has to do with a series of measurements, multiple measurements, and how close they are to one another. So you really can't have precision unless you have several measurements. Okay? Now we illustrate this with a dartboard. And we take a look at these three sets of darts. Someone's thrown 3 darts in dartboard A, B, and C. And ideally, if you're a dart thrower, you would want this to be what you are trying to achieve. If you see this pattern right here in the middle, you've got 3 darts clustered together. They're off center, but they are clustered together. And when we think about it, that the person who did this probably is repeating the same mistake over and over again. If they're aiming at the center and hitting high, there's probably something about their release point or something like that. They're being consistent, we'll give them that, but they're not accurate. If they were accurate, they'd be hitting the center. Now this person is consistent, we're going to use the word precise, and they're accurate in the sense that each one of their throws has hit near the center. Now this one over here has 3 throws. They're in very different areas and they don't seem to be clustered together either. So this is exactly what we want to avoid in every scenario, is not only not having any of our throws near the center, but not near one another either, which means we're neither consistent or reliable. The word we're going to use is precise. Or are we accurate? No, we're not accurate either. So in physics class, you want to be dartboard A. Now we're not throwing darts so much in class, so these are actually numbers. Every dart represents a number, and we're trying to hit a bullseye of a target number that number really is supposed to be. And if we get close to the actual number, we say it's accurate. And if we can repeat that over and over again and hit it multiple times, we'll say we're precise. Here's the way it would look on a graph. These are actually 4 students I had in the past, and these are their graph distributions. And the question is, are they accurate and precise? And it's kind of hard to tell unless you know what you're looking for. Okay? The patterns are somewhat linear for each one of them. This one is the widest spread, and Sarah let me use this as an example. She said she wasn't careful enough when she took her measurements, and so they were a little bit too high and a little bit too low, and when you get in a hurry, then it's harder to find the line that should go through the center. Now that's not the only judgment call you want to make, because over here, this one up here, James did a very good looking plot that looks very linear, and you may think of all the 4 plots, that one's probably the tightest one. And in a precision sense, this one clusters around a line the very best. But if you look at James's y-axis, his scale goes from 0 to 15, whereas everybody else goes from 0 to about 1.4 or 1.5. So James has made a mistake in his scale. Something's wrong about his number, so he's actually very inaccurate. He's about 10 times too big. Okay? Now let's compare Neil and Tim. They're very similar, but Neil's looks like a very pretty good cluster, but it's kind of raised. It's like the entire line has been shifted upward. Now it turns out in these cases that each one of these students made a mistake in technique in lab that caused the spread of data or the distribution of data to be somewhat off. So actually the best representation we have here is either Tim's or Neil's. Tim's actually spreads out and gets wider as he goes up like this, so he's like taking less and less care. And he told me in time that he had started here at the beginning of the lab, and then he got in a hurry and this spread out on him on the end. So Neil seems to be a little bit too high. Tim's spreads out. Sarah's is wide all the way throughout, and James has a very tight pattern, but it's inaccurate because his scale is wrong. So these are all things to watch out for in your own work when you work with precision and accuracy. Okay, so we're going to stop there for today because that's the summary of what has been in Chapter 1 that's on the test for this review unit. Okay, hope this helped. Sorry I couldn't be with you today, and I will see you after the long holiday weekend, and pray that you have a safe one and an enjoyable one, but don't forget to study and do your very best. Okay? Thanks.